Okay, welcome to AS 2017 paper 2. This is practical skills and multiple choice. As per usual, can't show the paper on screen, I'm afraid, otherwise AQA will get my channel deleted as they nearly did in the past. So first of all, we have these four resistors, 2.2 ohms, 3.9, 6.8 and 8.2. We're looking for the largest resistance with two resistors. Well, of course, we're going to have them in series and we're going to add them if that's the case. So therefore, we're going to use the bottom two, 6.8 plus 8.2 gives you 15 ohms. Next, what about the smallest with 2? If you want the smallest, then we know we want parallel, because we know that when you put resistors in parallel, current is shared across them, therefore reducing the resistance to less than the individual resistances. So therefore, if we have just two resistors like that, we can use the smallest resistors for that. So therefore, we're going to employ our equation 1 over R total equals 1 over R1. So that's 1 over 2.2 plus 1 over 3.9. So don't try and do it all in one go. Just get a value for 1 over R total first, and then just do 1 divided by that to get R total. And that gives us 1.4 ohms. So we see that V is equal to 1.62 when we have no resistors. Is this equal to the EMF? Yes, it is. Why is that? Well, it's because no current is flowing through the battery, or rather I should say power supply. Therefore, no energy is being lost due to internal resistance. We can say no volts lost in power supply. 1.4. We could have this combination here. Why is V less than 1.62? Well, that's because just the opposite of 1.3. So I don't really know why they're asking this as well, but there we go, easy marks. Current is now flowing, energy lost in it due to internal resistance, resulting in terminal PD being less than the EMF. Some volts lost in it. Easy peasy. Okay, we're given just a rejigged version of the internal resistance equation. First, we're being asked to find what the EMF minus the terminal PD is. And we saw earlier the EMF is 1.62. Let's take away the terminal PD from just now, and we end up with the value of 0.48 volts. That's the number of volts lost in the battery. And then V over R. It's just going to be our 1.14 terminal PD divided by the overall resistance. That was 2.2 plus 6.8. So it's just 1.14 divided by 9. And it gives us 0.13. What's the unit of that going to be? Technically volts per ohms, but we don't really care about that too much. That's not really a thing we deal with. 1.6, just a line of best fit and points. You guys know how to do that properly. Then 1.7, we're being asked to determine R. So let's have a look at our graph, and we know it is going to go through the origin, so they are proportional. So we have EMF minus V on the y-axis, and we have V over big R on the x-axis. So our straight line equation is y equals mx plus c. Therefore, looking at our graph, we know y is epsilon minus V, x is our V over R, and there is no y-intercept because, as we can see from our equation, there's no plus or minus here, at least apart from the minus at the beginning. So what does that mean? That means that R, little r, our internal resistance, that is going to be our gradient. So picking 2 points on your graph, make sure they're nice and far apart. That's the way you get a nice value. And don't forget, you have to use the line of best fit, not 2 points that are plotted, not 2 data points, and you end up with a gradient of around 3.7, and that is going to be ohms. Next, we're given the resistors in a square instead, where we can attach the two leads to A, B, C, and D. Is that better than the first method? No, it's not. Why? Because method 1 allows for more values of R, and we can say that method 2 only allows for, well, we could do 1, 2, 3, 4, and then diagonally as well, 5 and 6. So it only allows for 6 values. Whereas method 1, gosh, you could use any combination of them in series and parallel. You could have a vast number of different resistances. Mark scheme also mentions that actually we can have a greater range of values with method 1 as well, because you can have higher and lower maximum and minimum values as well. Mark scheme says then that actually the max that method 2 goes up to is 8.2 ohms if you attach it there and there at A and D. But they've forgotten that if you attach it there, then you have these other 3 resistors in parallel with that. So no, the resistance is not going to be 8.2 ohms if you attach it to A and D. Silly billies. So what do we have here? We have a pencil and we have the lead, quote unquote, but it's not lead, it's just a graphite core in the middle, and it has a diameter. And then we have the width of the pencil as well. So we use a micrometer to measure the width, and we use that because it has a very small resolution, and that's a good thing. And the resolution of a micrometer is probably going to be 1/100th of a millimeter. Very accurate, as W is going to be of the order of probably 10 millimeters, isn't it? 2.2, we have all these different values. We're being asked to find the percentage uncertainty in a mean. So first things first, let's find the actual or absolute uncertainty in the mean, and that is half the range. So let's take our maximum value, that is 7.23, take our smallest value, 7.06, divide that by 2, so that's 0.17 divided by 2, so that is 0.085. Technically that's millimeters. Okay, and then to get the percentage uncertainty, that's just going to be the absolute uncertainty divided by the mean. So that's our 0.085 divided by our mean. What's our mean going to be? All we do is add up all the values, then divide by 5 because there are 5 values. So I get a mean of 7.15. So that gives me 0.0118. Just round that up to 9. But then we times that by 100. That gives us 1.19%. We're given this equation. Area is equal to 0.83 times the width squared. Core is 9%, area of the whole pencil. And we're being asked to find what D is. Okay, so let's find out the area first of the pencil. So 0.83 times, well, the mean was 7.15, but that was millimeters. So we're going to times that by times 10 to the minus 3. That's got to be squared. That gives us an area of 4.2 times 10 to the minus 5 meters squared. But then 9%, that means we times by 0.09. And that gives us 3.8 times 10 to the minus 6 meters squared. So that's our area. We know that this is equal to pi d squared over 4. Therefore, rearranging this, d is going to be equal to the square root for 4 lots of this 3.8 times 10 to the minus 6 divided by pi. And that gives us 2.2 times 10 to the minus 3 meters, or in other words, 2.2 millimeters. 2.4, we're now measuring the length of the pencil. So we're just being asked how long is it. So looking at the vernier scale, first mark on the vernier scale goes past, what does that go past? 8 and then 5, so that's 85 millimeters. So it's 85 point something. And then which line on the vernier scale lines up with it? I'm going to say the 4th line lines up best. Therefore, the length is 85.4 millimeters. Okay, a bit of a weird one next. We're told that we are drawing 20 lines and each is 25 centimeters long. And then we're first being asked to find the new length, and I think that's 83.9 millimeters. Okay, so we're going to be looking at, no doubt, the difference in length. Let's do that real quick. Difference in length is just going to be 85.4, take away 83.9, so that gives us 1.5 millimeters. Okay, the next one, we're told that L half is the length of the line that can be drawn that would cause the original length of the pencil to be halved. So with these kind of questions, units are your friends. Coming up with your own units goes a long way and helps make things a lot clearer. So what we can say is that 1.5 millimeters of pencil And this is the problem, is that we're dealing with length of pencil and length of line drawn. That kind of sucks. I don't know why this is a 2-mark question. Could turn the length of the line drawn into millimeters, but because we're dealing with 2 lengths, let's keep that as centimeters. So let's go with 20 times 25. So that's 500 centimeters. Or in other words, 5 meters. So every 1.5 millimeters of pencil is lost per 5 meters. So I'll tell you what, let's divide that by 5 to turn that into how many millimeters we lose per meter. So 0.3 millimeters per meter drawn. Okay, next let's find out what half the length of the pencil is. So that's 42.7 millimeters. So we have millimeters per meter. We're looking for meters. So even if you don't understand what's going on, just looking at the units that we've got, we know we're going to have to divide them, and it's going to have to be the 42.7 divided by 0.3, because that's millimeters divided by millimeters per meter, so the meters end up on top. But let's try and understand what's going on here. We need to lose 42.7 millimeters of the pencil. Every 0.3 millimeters of that, we've drawn a meter, and that gives me 142 meters. Not an easy question, that one. All right, lots and lots of wordy stuff. We have a gravimeter, we have a mirror, blah, blah, blah. So basically we have stationary waves here, don't we? First we've been asked to find the wavelength, show that it's a certain length. So what can we deduce from the graph? Well, it's not a distance, so we can't just take that number. It is time, so we can find the time period. Time period is from one peak to the next. So that is 0.2 times 10 to the minus 14 seconds. Incredibly short times. For frequency, our wave equation is V or C equals F lambda, but we don't have frequency, we have time period. Frequency and time period are reciprocals of one another, so therefore we can say that V is equal to lambda over T. We just want to find lambda, so therefore lambda is just equal to the speed times the time period. So that's 3 times 10 to the 8 times 0.2 times 10 to the minus 14. I think we can do this one in our heads. Tidy up powers of 10. So plus 8 minus 14. So that ends up being times 10 to the minus 6. 0.6 times 10 to the minus 6. Or let's say 6 times 10 to the minus 7 meters. Okay, next we're being asked for the phase difference in radians. Well, let's look at the time difference between the two waves. Let's just pick one point. I'm going to pick equilibrium, 0.05 to 0.09. So that gives me 0.04. Now we're not concerned with the units too much because it's just all relative. Now phase difference is always just the bit divided by the lot. So difference in time divided by time period, difference in distance divided by wavelength. We're dealing with this, so therefore phase difference going to be 0.04. Yes, it's times 10 to the minus 14, but we don't care. All we then have to do is divide that by the full time period, which we said was 0.2. That will give us the number of complete cycles at the rate of phase, and all we have to do is times by 2 pi. So ultimately that gives us 0.4 pi radians. Okay, an equally weird question. So we get a max when mirror moves half a wavelength. So we have 2.37 times 10 to the 5 maxima. So therefore, if we times that by 2, we saw our wavelength earlier, 6 times 10 to the minus 7 meters. So therefore we can find out that we've moved the distance 2.37 times 10 to the minus 5 times half a wavelength. So let's do 6 times 10 to the minus 7 divided by 2. That gives us a distance of 0.0711 meters. Okay, so we have a distance, but what are we being asked to find now? We're being asked to find a value for A. So therefore we're going to have to use SUVAT. We're looking for A. We know that U is 0 because it was dropped. S, that's our distance, so that's that 0.0711. And we're told the time as well of 0.120 seconds. We don't care about V. So let's go with S equals UT plus half AT squared. UT disappears as per usual. Rearranging this, we end up with A is equal to 2S divided by T squared. So it's going to be 2 times 0.0711 divided by 0.120 squared. And it looks like we can go to 3 sig figs with this answer. It gives us a value of 9.88 meters per second squared. Here we have a graph. We're asked to find a gradient at a point when the time is 0.12 seconds. So that's about there. All we have to do is get our ruler, make it touch at that point. Make yourself a triangle, big triangle, and then find the gradient of the tangent. And the gradient should be equal to something like 1.2. What does this gradient represent? Well, we can see on the y-axis its distance, on the x-axis is time, so therefore gradient is going to be distance over time, so that is speed or velocity at that time. 4.1, we have this ion propulsion unit, blah blah blah, lots of things flying around. Let's just deal with the matter at hand. We have the mass of an ion is 2.18 times 10 to the minus 25 kilograms, and it is a xenon plus ion, so that means that it's just singly ionized, it's just missing one electron. So specific charge, also known as charge to mass ratio, just take charge divided by mass. So if you lost one electron, then that means the overall charge is just 1.6 times 10 to the minus 19. Some people quite often go for the total number of protons in a nucleus and then times that by 1.6 times 10 to the minus 19. Don't do that. Divided by 2.18 times 10 to the minus 25. Clear up some powers of 10. Let's make that into times 10 to the 6. And we end up with a big number, as we usually do for, or always do for a specific charge. Let's go to 2 sig figs, 7.3 times 10 to the 5. And the units of that is coulombs per kilogram. 4.2, we have the total mass of xenon. We have 79 kilograms. We have a power of 2.1 kilowatts. Energy gained by each xenon is 1,300 electron volts. We're going to have to turn that into joules. Why not? Let's do that now. So that's let's go to 2 sig figs, 2.1 times 10 to the minus 16 joules. And actually, that's all we're being asked to do for question 4.2, so that's nice. 4.3, how long was it on for before the xenon was used up? So let's just write down the mass of one xenon atom again. So first things first, we need to find out how many xenons. So we take our 79, we're looking for a big number of course, so we divide by a very small mass of each atom. That's 3.6 times 10 to the 26 atoms or ions, whatever. I'm told that each of those gains that much energy, so let's times by that. Gives us 7.6 times 10 to the 10 joules. So we have our energy, we have a power up the top there, we're looking for time. Power is energy divided by time, so therefore just swapping those two round. So that means time is equal to energy divided by power. So that's our 7.6 times 10 to the 10 divided by a power of 2,100 because it was kilowatts. And that gives us the 2 sig figs, 3.6 times 10 to the, that's a big number, that is times 10 to the 7 seconds. 4.4, what would happen if we used helium instead of xenon? So they've mentioned specific charge here, but we don't really care about that. All we care about is the mass. So helium is lighter. Now the Mickey Mouse way of saying it is therefore speed would be greater. As we know, EK is equal to half mv squared. They're gaining the same amount of energy, so therefore we could say that the mass would be inversely proportional to the speed squared, or rather V would be inversely proportional to the square root of 1 over m, or 1 over the square root of m. Now the thing is that we're trying to drive this spacecraft, whatever, and so therefore if we're trying to get it somewhere, we need to talk about things in terms of momentum. Now this is something that comes up fairly often, but it's something that isn't really taught very well quite often, and it's definitely something that students forget a lot because we don't do it that often. So how are EK and momentum related? That's a really good question, and it's something that is worth remembering how to do. So look, we know that EK is equal to half mv squared, and we know that momentum is equal to mv. I can just call that P. So what we do is we multiply both sides by mass, and we end up with half m squared
v squared on the right hand side, which is equal to momentum squared. Therefore, rearranging this, we can see that momentum is equal to the square root of 2 times the mass times the kinetic energy of a particle. Okay, so therefore, we know that if they're receiving the same amount of energy, then we can just get rid of that and a constant as well. So we can see that momentum is therefore proportional to the square root of the mass. So actually, xenon ions result in greater change in momentum, therefore higher thrust or higher force that is then propelling this spacecraft. So this whole momentum versus kinetic energy is something that's very, very useful, especially when it comes to year 2 actually, and then multiple choice as well. Finally, multiple choice, my fave. So we have a ramp, we have a height, we have the length, and we have that. But like I always say, if you have a height, it's going to be GPE is equal to KE, or something similar to that. It's going to be conservation of energy. So in this case, not all the GPE is being turned into KE, so there's an average frictional force, and so we know that some energy is going to be lost. So therefore we can say energy lost or work done. So this is mgh is equal to half mv squared. So GPE equals KE plus work done against friction, just force times distance. So we might as well do this all in one go. So I'm going to take half mv squared to the other side. I could also take out the mass as well. If I divide the whole lot by distance as well, that'll leave me with the force. Now what, I will take the mass out. So 2.5 is 9.8 times a height of 3 minus half times the speed squared. Divide that by the distance, and that's 5 meters. Let's be honest, when we're dealing with multiple choice, we can play fairly fast and loose with approximating things. So that's 2.5 times, well, let's say 10 times 3, so that's 30 minus half of 25, so that's 12.5 divided by 5. So actually then I can just replace that with 0.5, so it's just a half. So 30 minus 12.5, that leaves me with 17.5, basically then divided by 2. And so I think that should give me something like 8.75, and the one that's closest to that is 8.5, so it's A. Quite a lot of work for 1 mark, but that's the way that these multiple choices go. Which row is correct? Well, hadrons, so that's baryons and mesons, they feel both the strong and the weak. So therefore the answer is A. Might be tempted to just say just strong, but no, it is weak as well. Leptons only experience the weak force. And we want a current of 7.5 amps. So actually let's have a think about this. Let's find out what resistance we'd need for that current first, V being that EMF. We're looking for resistance, so resistance is equal to that EMF divided by current. So it's 1.5 divided by 7.5, and that is just 0.2 ohms. Now we're told that each internal resistance is 0.6 ohms, so therefore they can't be in series with each other at all. So it can't be A, and it can't be B. Looking at the EMFs as well, A will give you an EMF of 3 lots of 3.5, so 4.5. B will give you an EMF of 1.5 because 1 is turned round. So 2 cancel each other out, so we're left with 1.5. So it's either C or D. Now C and D, we could look at the resistances, but actually just think about EMF. C will give you 1.5 plus another 1.5 because of those 2 in parallel. So that will give you 3 volts, so therefore it can't be that. So it must be D. And sure enough, if you do the whole 1 over R total equation for those 3 resistors, you do end up with a resistance of 0.2. Okay, what do we have here? Beta minus decay. So we have nickel 65 decaying into something plus a beta particle. Don't care about the antineutrino, to be honest, not in this situation. So therefore the numbers left are going to be again 65, but the proton number's gone up. We don't know what it is. Let's just call it mystery isotope X. I can't remember what it is off the top of my head. So therefore we're going to have 29 protons, so that gives us 36 neutrons. So therefore the answer has to be C. Okay, so we have a gun and we have a bullet. We know that if it's recoil, we have conservation of momentum, but it's 0 momentum before, 0 momentum afterwards, so they're equal and opposite. First of all, like we said, we know the total momentum has to be 0, so it can't be B or D. But let's just rearrange this to find V1. So the mass of the bullet was 0.01 kilograms times that by the speed of 100, so ultimately that's just going to be 1, and then divide that by the mass of the gun, which is 4. So it's going to give us a velocity of 0.25 meters per second. So therefore it has to be A. Which one shows these in order of decreasing wavelength? So decreasing wavelength means increasing energy. So therefore we want to end up with gamma on the end. And actually, to be honest, I can see that it has to be C because that's the only one with gamma on the end. 11. Unpolarized EM waves. What happens? The wave remains unchanged. Well, that's not true, is it? The wave does not pass through the polarizer. Some of it does. The electric field oscillates along the direction of travel. No, it's 90 degrees too, so it has to be D, but let's just check it. The intensity of the wave is reduced, yes, by exactly half, because half of the waves are absorbed. Alright, what's the current in the 2 ohm resistor? So this comes down to V equals IR, but we have to decide what are we doing it for. Could go down the route of proportion of current going through each resistor, but I never like doing that. I think it's always best to use V equals IR. So let's do V equals IR for total values first. So what's our total going to be? 1 over 4 plus 1 over 2 plus 1 over 1. In other words, 7 over 4. Therefore our total is 4 over 7. And that ends up being 0.57 ohms. Therefore V total is going to be I times R. So that's 10 times that 0.57. So that's 5.7 volts. Now that we have that, let's use V equals IR again, but for the resistor, for the 2 ohm resistor, current is equal to V divided by R. V is the same as the total V because they're all in parallel with each other. So divide that by the 2 ohms and we should end up with 2 point something. So I reckon it's going to be B, and sure enough, it is. 13. I hate this question and this concept. It's very confusing. Quite often AQA get this wrong. So what's involved with the production of a strange particle and decay into non-strange particles? Now it's the strong force can produce strange particles. Weak is when they decay. So therefore it has to be A. That's just something that you have to remember. So we have a stationary wave. What's the phase difference between the oscillations? Well, it's 0, because with a stationary wave, points can either only be in phase or completely out of phase. Pi radians out of phase if they're above equilibrium as opposed to below. But these are both above equilibrium. It doesn't matter where these points are on the curve on the top, they're always going to be in phase with each other. So therefore the answer has to be A. 15. What's a scalar and a vector? Okay, momentum is definitely a vector, so it can't be A and it can't be C, and it's a vector because it has velocity in it, which in itself is a vector. So actually, well, just looking at the right there, we know that it can only be D. That's the only other one that says that velocity is a vector. Looks like moments to me. We're looking for the weight of the object, but we have the added thing of the ruler having a weight of its own. So therefore, we need to take into account that too. So we know this is 15 here, this is 60 here. Don't actually care about units because it's all relative. And then we know we also have the weight of the ruler. If it's from the pivot to there, then that must be 50, take away 15, so that has to be 35. And then we have an object here too. So we're told the weight of the ruler is 1.5 newtons. We're told that this here is 2.5 newtons. And then here we have, well, our force pulling downwards, but also the 0.5 newtons from the pan. So, gosh, they have made this one complicated, haven't they? So let's make an equation then. So F plus 0.5, and that's times 15, distance from the pivot. And then let's do our moments on the other side. So 1.5 times 35 plus 2.5 times 60. And let's sort this out all in one go. I can divide that by 15 on the other side, and then I can just take away 0.5 right to the end to be left with my force. So, and that leaves me with 13 newtons. So therefore the answer has to be C. A lot of work for 1 mark there. Good grief. Material that breaks without deformation. Well, it's brittle, isn't it? So it has to be B. Battery, no internal resistance. We have an EMF, so therefore actually just a voltage of 12 volts. We have a resistance of the heating element of 6.5 ohms. We're being asked what's the energy transferred in 5 minutes. So that's 5 times 60, so that's 300 seconds. Well, we know that power is equal to VI, I squared times R, but also V squared over R. That's what we're going to be using for this one. And then we know that power is also energy divided by time. Therefore, energy is power times time. So therefore, the energy is going to be equal to that V squared over R times the time. So that's 12 squared times the time of 300 divided by 6.5. And that gives us 6,650 joules. So it's going to be C. Okay, we have a force time graph. As soon as you see a force time graph, area under FT graph is equal to impulse, which is the same thing as basically gain in momentum. So what we can do is split this into a rectangle there and a triangle there. So therefore that's 4 times 10, so it's going to be 40. And then here, that's 6 times 6 divided by 2, so that's 18. Adding these two up here, we end up with 58 Newton seconds of momentum gain. So therefore the answer has to be D. Alright, looks like photoelectric effect. The power of the light is doubled. So we're going to assume that the frequency stays the same, so therefore the kinetic energy stays the same. So therefore it has to be A or C, so it can't be B or D. But we know that the number of electrons emitted per second has to be doubled because there's more photons going in. So therefore it has to be C. 21, what would happen if y has a higher work function than x? Well, we know the gradient stays the same because the gradient gives you Planck's constant, and that is a constant. Work function is just the y-intercept, so we're just talking about the line getting shifted up or down. The only one whose gradient doesn't change is A, so it has to be that. Which one shows a relationship between E and lambda? Well, we know that E is equal to hf, but if we're talking in terms of wavelength, then it's hc over lambda. Therefore, energy is inversely proportional to the wavelength. Therefore, if you have energy on the y-axis and wavelength on the x-axis, we must have the characteristic 1 over x curve. We don't have that at all, so therefore it cannot be A and it cannot be B. So let's have a look at C and D. They both have energy on the y-axis and 1 over the wavelength on the x-axis. So therefore, we know they must be directly proportional. So therefore, it must be D.
Okay, 23. What would happen to VF and lambda if a wave goes from optically less dense to more dense? So more dense means a higher refractive index. So that means velocity goes down. So of course we'd end up with the ray going like this and then going towards the normal, so the rays would start to bunch up like that. So the wavelength also goes down, but because we know that V equals F lambda or C equals F lambda, if V goes down but wavelength goes down, that means the frequency doesn't change. So the answer is C.
Okay, so we have refraction. Let's crack out Snell's law. We're looking for theta 2, and 1 is 1 because it's just air. Sine theta 1, be careful. They've given us the angle between the ray and the boundary. We want the other one. So actually we're looking for 55 instead. Equals N2, so that's 1.5 times sine theta 2. Get rid of the 1, 1.5 over there. Put it into my calculator and then inverse signing the answer. I end up with 33 degrees. So therefore it looks like the answer is going to be C. 25. Oh gosh, lots of words. Intensity maxima, blah, 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 blah. Light of a longer wavelength can be used, or the distance can be increased. What shows how the maxima changes? Okay, so you should know that just longer wavelength is synonymous with more diffraction, whether it's diffraction grating or Young's double slit. So therefore, it cannot be A, and it can't be D. So is it B or C? Let's find out. Distance from grating to screen increase. We know that they have a greater distance to spread out, so they're going to be more widely spaced as well. So it has to be B, doesn't it? Pretty easy one. What can't be used for the Young modulus? Well, the unit of the Young modulus is pascals, and that is the same as newtons per meter squared. So let's just have a look at the options that we have. Newtons per meter squared, so yes, that's correct. So it can't be A. B, we know it's pascal, so it can't be B either. Let's have a look. Newtons, we know F equals MA, so that's going to be kilograms, meters per second squared for newtons, and then times that by meters to the minus 2, so that actually gives us just meters to the minus 1. Is that an option? Yes, it is. That's D, so it can't be that. So it looks like the answer has to be C. Okay, diffraction grating. So a lambda of 500 nanometers, so that's 5 times 10 to the minus 7 meters. We have a grating spacing of 400 lines per millimeter. So timesing that by 1,000 gives us 400,000, or 4 times 10 to the 5 lines per meter. Therefore, 1 over 4 times 10 to the 5, I can see that's going to be 2.5 times 10 to the minus 6 meters. So let's get our equation. D sine theta is equal to n lambda. We're looking for sine theta, so we can say sine theta is equal to n lambda over d. We're looking for the second order, so we do 2 times the wavelength, 5 times 10 to the minus 7, divide that by 2.5 times 10 to the minus 6. Can we do that in our head? I reckon we can. So that's going to be 10 times 10 to the minus 7, but sorting out powers of 10, we're just going to end up with minus 1 on top, so therefore that's just going to be 1, so that's going to be 0.4. And that gives us 24 degrees, but they've been cheeky. They said, what is the angular separation between the two second order maxima? So actually we're looking for this angle here when we've just got theta here, but we're looking for 2 lots of that. Therefore, the answer has got to be 2 times 24, 48 degrees. So I can see the answer is basically D. Okay, 2 identical balls, 25 centimeters apart. Okay, this is confusing, isn't it? So it goes like that, and then the other one is projected that way, is that right? Yeah, it looks like it. What is the distance 1 second later? Oh, good grief. So we need to know how far this one's gone in 1 second. Okay, so speed equals distance over time for horizontal, because there's no air resistance. We're not talking about vertical here, just horizontal. We're told the horizontal speed to begin with is 0.1 meters per second. So distance equals speed times time. So that's 0.1 times 1 second. So it's just gone a distance of 0.1 meters. In other words, 10 centimeters. So they were 25 centimeters apart. Now they're 15 centimeters apart. So therefore, the answer has to be A. Seems like it's going to be a lot more complicated to do with SUVAT, but no, they're trying to catch you out there. 29. Elastic collision, no external forces. If it's elastic, we know that total KE is conserved. So therefore, well, we know it has to be A or B, but magnitude of forces greater on the smaller mass. No way, it has to be the same on both, doesn't it? Because that's just the way forces work, Newton's third law. So it has to be A. So we have 2 wires. Which statement is incorrect? So A, for a given extension, more energy is stored in X than Y. That is true because it has a greater area under the graph, so therefore it can't be that. B, the Young modulus of Y is greater than X. No, that has to be false, doesn't it? Because it has a lower gradient, so it has to be B. And C, they obey Hooke's law. Yes, that's true, because they haven't gone past the elastic limit. And X has a greater breaking stress. Yes, because it's just higher, isn't it? Higher force at the end. 31. What is correct about superconductors? When a material becomes a superconductor, its resistivity is almost? No, that's what people get confused about sometimes. It is precisely 0. Temperature at which a material becomes a superconductor? Yes, that's true, isn't it? Critical temperature, below that, it's a superconductor. Current is passed through, PD becomes a maximum. No, that's nonsense. And D, copper is a superconductor. Pfft, nope. It's good, but not even close. 32. Y has resistance R. What is it when the length and radius are doubled? So it looks like we're cracking out our resistivity equation, R equals rho L over A. We're not concerned with rho because it is the same material, so we can say that R is proportional to L over A. But we know that area is dependent on radius or diameter squared, so therefore resistance is proportional to length over radius squared. So if this is doubled, but this is doubled, then this whole thing goes up by times 4, so actually the whole thing goes down by a factor of 2. So therefore the answer has to be B. 33, we have a thermistor. We know that for a thermistor, resistance goes down when temp goes up, and so it can't be A and it can't be B. But also we know that it's not just going to be the straight line, because of course we can't just have the resistance just going straight to 0. It is going to sort of curve out towards the bottom there, almost exponentially. So the answer has to be C. And then finally 34, we have an LDR. Well, we know that similar to a thermistor, When light intensity goes up, resistance goes down, shaking them electrons loose, as it were. So if the resistance decreases, then that means that the current must increase because the overall resistance has decreased, so therefore it can't be A and it can't be B. But we know that because the resistance goes down, we know the voltage share across it also goes down because it's a potential divider. Here we have two resistors, so therefore the answer must be D. So, hope you found that helpful. If you did, please leave a like, and if you want to see some other papers, then check out the playlist and you'll find loads there. See you next time.